As we know, fossil fuels are burned to produce energy. In large power stations are burnt in presence of oxygen. As the fuel burns, the heat energy is used to heat water. As it is heated, produces steam which in turn rises and drives a turbine. So instead, we use renewable source of energy. Further, nanotechnology provides solution to the most important problems of renewable energy system. The low efficiency of renewable energy system can be improved through the use of nanomaterials. Also, nanotechnology can be used to improve renewable energy sources. For example, wind energy efficiency can be improved by using light, more strength nanomaterial for rotor blades. In biomass energy, using nano-based precision framing to optimize crop use to produce biofuels. As the property of nanomaterial differ from the bulk phase, it can have an astonishing impact on their catalytic property in various reactions, including photocatalytic water splitting for hydrogen production. Nanoferrites have been reported for the thermochemical splitting of water for hydrogen production. However, these processes operate at high temperature, making the process energy intensive. In continuation of our work on advanced nanomaterial for sustainable catalysis, here in we report nano Fe3O4 as an excellent catalyst for hydrogen production through water splitting, the principal continuation of our work on advanced nanomaterial for sustainable catalysis. It has shown high potential in hydrogen production with an exceptionally high rate of catalytic hydrogen evolution. The influence of various operator parameters was also studied and optimized. So now the question arises, how do we prepare nanoferrites? Nanoferrites were prepared by co-precipitation method using FeSO4.7H2O and Fe2SO4 taken twice in water. In 500 centimeter cube of water, 13.9 gram of ferrous sulfate in 7H2O and 20 gram of Fe2SO4 taken thrice were dissolved. Ammonium hydroxide 25% was added slowly to adjust the pH of the solution to 10. The reaction mixture was then continually stirred for 1 hour and then precipitated nanomaterial were isolated, washed with water until the pH reached 7, and then dried under a vacuum at 60 degrees Celsius. The catalysts were characterized by X-ray diffraction, which confirms the formation of single-phase Fe3O4 nanoparticles. Here is a picture which shows transmission electron microscopy, popularly known as TEM, image of Fe3SO4. Transmission electron microscopy also shows nanoparticles with spherical morphology and size range of 10 to 12 nanometers, which is comparable to the crystallite size calculated from X-ray spectrum. The corresponding SAED patterns of Fe3 particles. Photocatalytic water splitting of water by nanoferrites in the presence of sacrificial donor and platinum as co-catalyst was carried out in the tabular borosilicate glass reactor. The experiment setup was same as that employed by Mangrulker. The hydrogen evolution rate was observed to be about 8.275 millimolar with a hydrogen yield of 8275 millimolar for nanoferrite, which has significantly higher as compared to the hydrogen evolution rate. So it has wide application in terms of hydrogen. So here are some parameters which affect the reactions. So we'll be looking about the effect of amount of catalyst, effect of illumination intensity, effect of irradiation time, and effect of reaction temperature. Here in the effect of amount of catalyst. The amount of photocatalyst used in vital parameter in all photocatalytic reactions. The effect of amount of nanoferrite on photocatalytic hydrogen evolution was studied in the range of 0.5 to 10 mg per 20 ml of water. The hydrogen in with respect to varying doses. It was observed that initially the photocatalytic activity increased with increase in the photocatalytic dose up to 1 mg and later on the activity decreases with the increase in dose. At a low dose, the number of active sites is also low, resulting into lower hydrogen evolution. So, effect of illumination intensity. The effect of illumination intensity on the catalytic activity of nanoferrites was investigated. However, the hydrogen yield increased with increase in the illumination intensity, and with the effect of radiation time, the photocatalytic hydrogen evolution of nanoferrites was studied by varying the radiation time. The decrease in the hydrogen evolution can be attributed to the exhaustion of the sacrificial donor, as in the batch system a progressive decline in the hydrogen evolution is observed on increased radiation time owing to the backward reaction as well as the pressure buildup in the gas phase. Here, the reaction was carried out in three different temperatures, mainly at 30 degrees Celsius, 75 degrees Celsius, and 100 degrees Celsius. Here, the temperatures observed to play an important role in the enhancement of the photocatalytic activity of nanoferrites in water splitting reaction in the presence of sacrificial donors. And now, the characterization. The phase of nanoferrites was determined by X-ray diffraction in an MMS X-ray diffractometer with a Cu copper Ka source in the 2G range of 10 to 70. The data was collected with a step of 1 per minute. TEM micrographs were recorded on an Philips CM20 TEM microscope at an operating range of 200 kW. Diffuse reflectance UV spectra of nanoferrites was recorded on Perkin-Elmer spectrometer lambda 900 equipped with an integrated sphere. Barium sulfate was used as a reference material. Further applications of ferrites. Hydrogen production via water splitting by nanoferrites was studied using ethanol as a sacrificial donor and platinum as co-catalyst. Nanoferrite is emerging as a promising photocatalytic with a hydrogen evolution rate of 8.27 micromole hour inverse and a hydrogen yield of 8275 micromole hour inverse gas inverse under visible light compared to 0.0046 micromole hour inverse for commercial iron oxide tested under similar experimental conditions. Nanoferrites were tested in three different photoreactor configurations. The rate of hydrogen evolution of nanoferrites was significantly influenced by the photoreactor configuration. Altering the reactor configuration led to seven-fold increase in the hydrogen evolution rate. So these were my views on application of ferrite nanomaterial in solar water splitting. So thank you.